Hello everyone. So what you see here at the top is a problem that somebody sent me from our assignment on my math lab. And I think it's a good problem to do, and I want to show you how to do it. So here goes. It's a definite integral. I've got sine squared 2 theta. Bounds are theta is negative pi over 2 to positive pi over 2. And I've got the answer right there. And I'll discuss two parts to solving this. One is using the fundamental theorem of calculus, and as part of that, finding just the antiderivative. All right, so let's talk about it. So I've got this integral. I'll divide it into part 1 and part 2. Part 1 is just to find the antiderivative. Okay? The reason I do that is because, as I was mentioning just a second ago, our ultimate goal in evaluating a definite integral is to use the fundamental theorem of calculus. And that looks like this. If I've got this function in there, sine squared of 2 theta, then I can evaluate this definite integral by just figuring out what is the antiderivative of sine squared 2 theta and evaluate between the bounds according to the fundamental theorem. Okay? Now, all right, so that's my first step. That's my first objective, is to find that antiderivative. But that opens like a much bigger question, is how do you find the antiderivative? Is there a certain technique you're supposed to use? So that's a big question, and just about every topic up to our first test will be about different techniques for finding antiderivatives. Okay, so far here's what we've learned. You can sometimes use trig identities or algebra to simplify what the integral looks like, and maybe through that it becomes apparent what to do. Another technique is u-substitution. Another technique we've learned is integration by parts. And then there's way more techniques than that. There are formula tables, and let's not forget that, like, there are so many ways that you could just use technology of one form or another to answer it. So here I went to Wolfram Alpha, and I'm not saying this is the only way to do it, but I just typed in what is the definite integral of sine of 2 theta squared from theta's negative pi over 2 to pi over 2. I typed it in, gave me the answer right away, exact form and rounded, and it also gave me just what the antiderivative is. So, I mean, you could do that, but we're not quite to that point where everybody's going to do everything in the class just by calculator or technology, software, whatever, okay? So even though that's on the table, and there are times when I think that's okay, generally I think you should expect to apply some technique on paper where you're thinking through things, you're making the decisions, you're making a judgment about what to do. That's the way our class is, at least right now, okay? Maybe in a few years, what calculus class looks like will be very different than it is now. Who knows? But right now, this is what we got to worry about. Okay, so of these techniques, how do you know what to do? All right. Before I show you how it works out, I mean, how do you make that decision? And if you being in class, you're confronted with how do you solve this problem? You make the decisions, you decide on the technique, you go through the analysis and so on. How do you know what to do? I think it comes down to either insight or practice and experience, okay? If you have insight, you're just so smart that it's obvious to you what to do. Some people are like that. Or maybe you're like that some of the time. If that's not the case, if you look at these kinds of things, you're like, I just don't know how you decide what to do. How do you know which technique you're supposed to use? Well, from there, I would say practice or experience. Okay. If you see enough problems, even if they're a complete mystery to you the first time you see them, if you see and practice enough, you'll begin to recognize certain kinds of problems lend themselves to certain kinds of techniques. Okay. So I think that's what it'll come down to. I think most people might be a little bit in one camp or the other, depending on what they're doing. But for most people, there's going to be a fair amount of practice and experience that's required. Okay, so the way that we solve this one is we use a combination of applying just the right trig identity and then using u-substitution. Here's what that's going to look like. For this integral, in order to find just the antiderivative, I'll apply this identity. Sine squared of an angle is 1 minus cosine of double that angle over 2. You can find that in a resource I provided you. If we go to Canvas and we look under the Test 1 module, there's this formula sheet, suggested formulas for Test 1. And as far as you working things out on paper, I want you to use anything that you can find here. And if it's not on here, you're going to work out the rest of it, okay? So let's see. I do have some standard trig identities that you'll make use of. And the one that I just showed you that I said will work for this particular problem is right here. Sine squared of an angle is 1 minus cosine of double the angle over 2. That's the identity that makes this one work out to be a u-substitution problem, okay? All right, so back to the problem. I apply that. In terms of sine squared of 2 theta, that's going to look like 1 minus cosine of 4 theta, because this angle is double whatever that one is over 2. Then I want to split this up into two terms. For this entire quantity to be divided by 2 means each term on top is divided by 2, and then we're looking at that. Okay, so what did the identity do for us? It turned this into that, but how does that help us? This is amenable to u-substitution. If I let u be 4 theta, this becomes a very basic kind of integral. This will become cosine u du through this substitution. What's special about that? Well, let's go back to the formula sheet. I have some standard forms of integral on this thing. Okay. And cosine u du is one of them. Okay, got it working again. So here it is. So here are some standard formulas that you can make use of when you see them. And through that u-substitution, I can get this one to show up. I can make that integral that I'm working on become cosine u du, which has an answer right here of sine u plus c. So that u-substitution makes this apparent, all right? Okay, so let's see. So there's my u-substitution. I'll let u be 4 theta. As a consequence of that, I'll let du be 4 d theta. And then I've got to make these substitutions work. I can obviously put u right here for 4 theta. What about the d theta? I got to substitute that somewhere. My substitution as I initially get it says 4 d theta. That does not say 4 d theta. It's just d theta. So in order to make this apply to that the way it is, I'll divide both sides by 4. And I'll let u be 4 theta like that. Okay, now I got u. And I'll let d theta be du over 4. Now the integral is in terms of a new variable, u. Now from here, the way different people simplify these things might look a little bit different. Everything I showed you could be varied a little bit, but here's what I'll do from here. I have a factor of 1/2, and I also have a factor of 1/4. What the numbers that's sitting in here are 1/2 times 1/4. So that's a factor of 1/8. If I were to redistribute this 1/8, I'd get back here. Okay. Since it's a constant, I think it's easy to just take it out. All right. I get that. Now these I know the antiderivatives of. Okay. So what's 1, the antiderivative of 1 with respect to u, if u is the variable? The antiderivative of 1 is u, because the derivative of u is 1. Now that's if u is the variable, which it is now. So the 1 becomes u. What about cosine u? Well, to get that is the whole reason I applied this substitution, because I happen to know, if I look at my formula sheet or I know my basic formulas, the derivative of sine u is cosine u. So there's my antiderivative, u minus sine u. From here, what I think people would often do is put this back in terms of the variable we started with. We introduce u so that the integral becomes workable. But u is not the variable we started with. Theta is the variable we start with. So I put this, which is in terms of u, back in terms of theta. I do that by just letting u be 4 theta, and I get that. So there's your antiderivative with the constant of integration attached to it. Now from here, I use the fundamental theorem of calculus. I have my definite integral I started with. There's the antiderivative I found, okay? And whenever I use the fundamental theorem, I don't have to put the plus c. If I did, it would just cancel out anyway. And then from here, I put pi over 2 first, negative pi over 2 second. That's the way the fundamental theorem works. I do my calculations, I get pi over 2, and I'm done. That's the answer. Okay? That's, of course, the answer you see here is the correct answer. It's the correct answer Wolfram gave me, or whatever calculator or program or website you want to use. If it's right, it'll give you pi over 2. Okay. Now, from here, I say I'm done, and that's fine. If you're happy working it this way, then I'm happy with it. But there's something I should mention. It would be bad if I left this out altogether, because maybe when you learn Calculus 1, you were shown to do like this. Okay, so here's a slight variation on what I just showed you. So it's regarding this part right here. Can I leave this antiderivative in terms of u? Like back when I was working on this part, I said, well, if we start with the variable theta and we convert to u so that we can work this thing out, it makes sense to put our answer back in terms of theta. And I guess it does make sense to do that, but you don't have to. I could leave this in terms of u and work from there. So think of it like this. We have this integral. It's in terms of the variable theta. Theta is the variable. Okay, the bounds of integration are theta. You plug in for theta, negative pi over 2. You plug in for theta, pi over 2. Then I made this u-substitution. If I want to, I could convert the bounds to u also and not have to change it back into theta in the end. So in other words, I've got my integral right here. Through my u-substitution, I turned it into this. But I'll go ahead and turn the bounds into u also. So it works like this. Let's say, okay, my substitution, u is 4 theta. If this lower bound was theta is negative pi over 2, then convert that over for u like this. We'll say, okay, if theta was negative pi over 2, u is 4 times that number. If you take 4 times negative pi over 2, you get negative 2 pi. So that lower bound is now in terms of u. Its u is negative 2 pi. Same thing with the upper bound. If theta was pi over 2, and if u is 4 times theta, then u becomes 2 pi. So there's your upper bound. So from there, when you find that antiderivative right here in terms of u, you can put those boundaries in as converted to u. And I guess it might save you a step. I don't think it's a big deal that you do that or not, but I should mention it. Okay. All right. So there's the big picture for this one. Okay. Hope all that makes sense. If it doesn't, if there's something we need to review here, such as trig identities or algebra, if you're messing up the constants or so on, then we need to iron out those mistakes too. Other than that, decide if you fall in the insight or practice and experience group. And from there, you might decide that you have to put in quite a bit of practice. When you work the assignment on My Math Lab, you can solve the problems, you can regenerate them. If you miss them, you can try them again. It will give you slightly different numbers. And I think that itself is a good way to just get a lot of practice in.